Now, as we know, objects don't always travel at the same rate, right? Like if I'm driving to work today, I might speed up to 60 kilometers per hour, right? And then I see a red light coming up, I might press the brake and slow down to 0. So in that case, I'm accelerating, I'm decelerating, I'm changing the speed, okay? I'm changing my velocity. We call this non-uniform motion, and a good example of non-uniform motion is something called acceleration. So acceleration is defined as a change in velocity, okay, during a specific time interval. Now, acceleration is a vector quantity, which means we have to have a number, a magnitude, and we have to have a direction. All right, so what we learned in the last lesson, up, down, west, east, north, south, right, left, they all have, those are all directions, okay? Some of them are negative directions, some of them are positive directions. So an accelerating object can either be changing speed or direction or both. Now, the formula for acceleration is A is equal to delta V over delta T. You'll notice that there are arrows over the A and the V. This means that these are vector quantities. So acceleration is a vector, and we use velocity, not speed, okay, because of the vector sign. So acceleration is measured in meters per second squared. Velocity is measured in meters per second, and the change in time is measured in seconds. Again, remember, acceleration is a vector. It must have a direction as well. Now, what is this meters per second squared thing? Well, if we take a look at what's going on in this formula, what we're doing is we're taking the velocity, which is measured in meters per second, and we're dividing by time, which is seconds. Okay, if we divide this fraction, meters per second by seconds, basically what we're doing is we're multiplying the seconds together, okay? And a second times a second is a second squared, right? So that's how we come up with this meters per second squared thing, okay? Because acceleration is described as the rate of change of velocity. So how is its velocity, meters per second, changing over time, over seconds, okay? So that's how we get our unit. Now, just like I taught you in the last lesson, okay, a lot of this stuff, you guys, comes down to organizing yourself. So just like speed and velocity, generally you will get 3 marks for an acceleration question, okay? 1 mark, easy mark, comes from writing your variables down. A is equal to delta V over delta T, okay? So remember, you guys, as I mentioned last time, delta can be expanded out into final minus initial, okay? So delta V can also be represented as velocity final minus velocity initial, okay? So keep that in mind, because remember, acceleration is a change in velocity. So anytime we see that delta sign, we can always expand it into final minus initial. Okay, so let's take a look at the variables in my question. It says, a car accelerates from rest. So that means the car is, let's say, stopped at a red light. Okay, so it's stopped at a red light. That would be its velocity initial. Okay, so the velocity initial of this car is 0 meters per second. This is rest. Okay, it's stopped. Now you hit the accelerator, the car speeds up, and it speeds up to a final velocity of 100 kilometers per hour, and we have a time. It takes that car 6.00 seconds. Now, when I write my variables down here, one of the reasons, you guys, is to organize yourself. Okay, another reason is to make sure that your units are all cooperating with each other. Can I divide my velocity by my time if I have hours in my velocity and seconds in my time? No. So I have two choices here. I can turn seconds into hours, or I can turn kilometers an hour into meters per second. Now, they've been nice enough in the question just to tell you what that is. Okay, so it's 27.8 meters per second, and the car is speeding up to the east. Okay, now what we're looking for in this question is the acceleration. Okay, so acceleration is equal to VF minus VI divided by time. VF is 27.8 meters per second minus 0 meters per second divided by 6.00 seconds. Okay, so my acceleration would be, the acceleration would be 4.63333, repeating, meters per second squared. Now, there's a couple of things wrong with my answer here. Obviously, number one, my significant digits are not correct. But look, I can look at my variables that I've written down, and I can see that my answer should have 3 significant digits. By the way, 0 is, we don't count it with significant digits. It's basically an infinite amount of significant digits, so it doesn't count. Okay, so 27.8, 3 significant digits, 6.00, 3 significant digits, so my answer should also be in 3 sig digs. And I'm also missing something else here, you guys. What am I missing? I am missing the direction. Because acceleration is a vector, I have to say that this is accelerating to the east. All right, so I just make sure, okay, I have my variables, that's 1 mark. I have my formula and I didn't have to do anything to it. That's another mark. I have my answer with sig digs, units, and direction. Another mark. 3 out of 3 for me. Now, there are 3 practice questions in your note package. I'm going to give you a few minutes here to try those, and then we will do them together and see how you did. Okay, and then we'll move on. So take a couple of minutes here and try those questions. All right, so you had a chance to take a look at these. Let's go through and see how you did. Space Shuttle accelerates from rest to a velocity of 50 meters per second upwards in 4 seconds. So remember, you guys, rest is always 0 meters per second, okay? So in this case, the Space Shuttle is starting out at 0. It's not moving, and then the thrusters hit, and in 4 seconds, it's going 50 meters per second, okay? So our initial velocity would be 0 meters per second. Our final velocity would be 50 meters per second going upwards, and our time is 4 seconds. What is the acceleration? All right, so I write down my variables, VI, VF, and T. I write down my formula, so A is equal to VF minus VI divided by T, and I just plug in my numbers. Okay, so just trust yourself, write down your variables, and just plug them into the formula. So we end up with an acceleration or a change in speed of 13 meters per second every second going upwards. So what that means is, in the first second, the Space Shuttle is going 13 meters per second. In the second second, the Space Shuttle is going 26 meters per second. In the third second, it's going 39 meters per second. So every second, its speed is increasing by 13 meters per second. Okay, that's what acceleration is. So it's getting faster and faster and faster and faster. That is not uniform motion. Now 2 sig digs, because my 50 meters per second has only 2 sig digs. Okay, it's speeding up, so it's a positive acceleration, and it's going upward. Okay, so 3 out of 3. Practice problem 2. A baseball is thrown at 25 meters per second. Okay, So it is traveling in a positive direction, and it is traveling at 25 meters per second. Okay, that's its initial velocity. It hits the catcher's mitt and stops. So its final velocity is 0 meters per second, okay, in 0.500 seconds. What is the magnitude of the ball's acceleration? Okay, now this might seem a little bit confusing. What does that mean? Well, again, write down your variables as is. So it's initially traveling at 25.0 meters per second. Its final speed is 0 because the catcher caught it, and it took 0.500 seconds for it to go from 25 to 0. Okay, so it's obviously slowing down, right? So it's not uniform motion. So we just write down our variables, you guys. We plug them into our formula, and some of you might be like, wait a minute, this doesn't seem right. How do I have 0 minus something, right? Shouldn't it be the other way around? No, we wrote down our variables, you guys. VF goes here, VI goes here, and what we end up with is a negative acceleration. So what does a negative acceleration mean? It means that something is slowing down, okay, like this ball, or it means that something is speeding up in a negative direction. So if I were to hit the accelerator and speed up to 100 kilometers per hour, but I was going west, that is technically negative acceleration, okay? So if something is slowing down or accelerating in a negative direction, all right? So a negative number for acceleration is just fine. Practice problem 3. A car driver applies the brakes and slows down from 15 meters per second east to 5 meters per second east. So it's slowing down, right? Right away, this kind of gives you a clue into what your answer is going to look like. Since our final velocity is smaller than our initial velocity, okay, so again, write down your variables. Trust yourself, okay? The car was initially going 15.0. The brakes were applied. Its final velocity was 5.00, which is slower. So what did it do? It slowed down. So what does that mean for our answer? It means that we're going to have a negative acceleration, okay? And be sure to put the direction in there, okay? So this person is traveling east. They hit the brakes. They're slowing down. That means that their speed or velocity in this case is getting less as time goes by. So that's why we have the negative 2.50 meters per second squared, because it's slowing down, okay? And it's traveling east. So don't be scared if you have a negative acceleration, okay? It can mean a few different things. Okay, so we have to handle falling objects and objects that are being thrown or shot in the air a little bit differently. And that's the reason for this is the pull of Earth's gravity. Okay, so if you were to drop a bowling ball out of a third-story window in an apartment building, okay, it's going to start in your hand at rest. When you let that bowling ball go, not throwing it down, but just letting it go, okay, that bowling ball is going to start to fall toward the Earth's surface because of gravity. Now, gravity is pulling on that bowling ball, and every second it is speeding up because of gravity, okay? Same thing with things that you throw up in the air. If I throw a ball up in the air or kick a ball up in the air, it is going to slow down as it rises until it hits 0, and then it's going to fall back down, okay? So we call this the acceleration due to gravity. Okay, the acceleration due to gravity is the same regardless of an object's mass. So regardless of whether an object is, weighs as much as a feather, or an object weighs as much as a bowling ball, the Earth's gravitational pull is the same on both of them. Okay, mass does not matter. Gravitational pull is the same. Heavy objects accelerate at the same rate as light objects. Now, here's the kicker, you guys. Assuming they have the same air resistance. Now, obviously, if I were to drop a bowling ball out of a window and I were to drop a feather out of a window, which is going to hit the ground first? The bowling ball. But I thought I just said gravity pulls on them both the same, regardless. They do, but the feather has more air resistance, so it's going to fall slower. If this were to happen in a vacuum, they would both fall at exactly the same rate. And the rate that things fall on Earth is 9.81 meters per second squared down. Anytime something is falling, okay, we use this as the acceleration. 9.81 meters per second squared. This is the acceleration due to gravity. So what this means is, after the first second, if you were to, let's say, jump out of an airplane because you're gonna skydive, after the first second of free fall, you're traveling 8.1 meters per second. After the second, you're traveling 19.62 meters per second. You guys get the point, right? Every second, your velocity is going to increase by 9.81 meters per second. Okay? So whenever we have a question where something is falling, okay, we are always going to use the value 9.81 meters per second squared downward, or is there another way I can represent that? Negative 9.81 meters per second squared, okay? So let's take a look at an example. A skydiver steps out of a plane and accelerates toward the Earth. If the skydiver free falls for 3 seconds, what velocity does the skydiver reach when the parachute opens? Okay, so let's write down our variables. The variable for time is 3.0 seconds. Okay, that's the time that the skydiver is free falling. Now we are assuming there's no air resistance. Okay, in these questions we're assuming no air resistance. What is the acceleration that this skydiver is falling at? Earth's pull on this skydiver is negative 9.81 meters per second squared. Okay, the negative means downward. And what we want to know here is what speed, or well, what velocity does this skydiver reach after 3 seconds? Okay, so my formula with acceleration, velocity, and time, okay, my base formula is acceleration is equal to velocity divided by time. Okay, I need to isolate this, so I'm going to find velocity. What do I need to do to this equation to isolate v? I need to multiply by t. Okay, that's going to cross off t on this side. What I do to one side, I have to do to the other. So velocity is equal to acceleration due to gravity, okay, times time. Okay, acceleration due to gravity is always negative 9.81 meters per second squared. And time in free fall is 3.0 seconds. And I end up with a final velocity after 3 seconds of, okay, the final velocity of this skydiver after 3 seconds is going to be 29 meters per second downwards. Okay, so I can either say like this, or I could have written it as just negative 29 meters per second. Okay, by the way, you guys, this is over 100 kilometers per hour. All right, so without air resistance, the Earth's pull is pretty strong, and you would continue to accelerate. Every second, you'd go another 9.81 meters per second. Okay, so without air resistance, you would be going really fast by the time you'd hit the ground. Okay, so again, we see here we have to rearrange our formula, and anytime we're dealing with falling objects, we use the acceleration of negative 9.81 meters per second squared. All right, so I would like you to look at the homework on page 12 of your note package. Remember, the key is to be found on the Google site.